Quite. This is Dr. Mohan Lakshmi, Professor and Head, Department of ECE from Rohini College of Engineering and Technology, Kanyakumari District. So, in the earlier lecture, we have seen about the small signal analysis of a BJT, and in this lecture, we'll see about the small signal model of a MOSFET. Okay, so using MOSFET, also you can develop a small signal model. So, MOSFET analysis. So here the various parameters, right? So we know that MOSFET involves again three terminal: gate, drain and source. Okay, so VGS, that is your voltage of gate source, will be very much greater than or equal to VT. Okay, in case of induced channel. In case of a continuous channel, the gate drain voltage will be greater, and okay, so here we have for the boundary, we have it for the pinched off channel, then you have it for a saturation region. So where at the saturation region, so this could be given as your drains current will be equivalent to the source current and gate current will be equal to 0. So of course we know that we have an induced channel, or it could be a continuous channel, or it can be at the boundary level. Okay, so here this is a large signal equivalent circuit model of an n channel MOSFET. Okay, so this operates in the saturation region. Okay, so here what is overdrive voltage? Overdrive voltage, here it is given as V, which represents an overdrive voltage, which will be equal to VGS minus VT, and from this I can write an expression for a gate source voltage. Okay, so which will be equal to VT plus VOV. And here operation in the saturation region. So when I operate in the saturation region, I should consider two conditions. Okay, so one is VGS should be very much greater than or equal to, or it is not very much, it is greater than or equal to VT, and similarly the VOV should be greater than or equal to 0. The second condition is gate drain voltage should be less than or equal to VT, and VDS should be greater than or equal to VGS minus VT. So I can say that VDS should be greater than or equal to VOV. So these are the two conditions. Okay, so in either case VOV should not be, mostly it should be greater than 0. Okay, so this is actually the model represented over here, and here you can see here gate source voltage, which is mentioned as VGS. There is a gate current IG and similarly drain current ID, and we have the conditions over here, which is VGS greater than or equal to VT, and similarly VDS is greater than or equal to VGS minus VT, and you have the current flowing, which is given by the expression which is put in the blue square box. So R0, that is your output resistance, will be equal to VA by ID. Okay, so here I could see what is, you can write what is overdrive voltage and what is VSG. Okay, and conditions for operating in the saturation region. So it is of course put up in the for the P channel. Okay, so the earlier we have seen for the N channel, this is for the P channel. So conditions for operating in the saturation region, we have VGS is less than, so there we have seen all thing, it is greater, here it is less than equal to VT, and similarly that is source drain voltage should be greater than or equal to the mod of the VOV. Okay, so again for the P channel it is represented here, R0 is again given by VA by ID. Okay, so the other parameters are shown over here in the circuit above. Okay, so large signal model, so the both the things were taken and it is put up in the same slide. So large signal model of a MOSFET, you can see what is has been represented. Okay, so here Ig will be equal to 0. You have a flow of drain current, one is which is flowing in, one is flowing out. Okay, and the representation you should be very careful. So it is either drain source or source drain, and similarly it is gate source or source and gate. So those things, it depends whether it is an N channel or a P channel respectively. So this is a transfer characteristic of an amplifier. You can see here the Q point which is acting in a cutoff region, saturation region, the other in the triad region. So here the slope at Q, right? So that you determines the voltage gain. Okay, so this refers where you need to plot the Q point. Okay, so the slope is determined over here, that is at the end of cutoff and the beginning of saturation, and similarly the end of saturation and the beginning of triode is represented as the point A and B, and the mid of this is taken as a Q point. Okay, so how do we conceptually we can utilize this to study the operation of MOSFET as a small signal amplifier? So the DC biasing point ID can be given as half Kn, it's a constant, W by L VGS minus VT the whole square. So I can say VD is equal to VDD minus IDRD to ensure saturation region operation. So VD should be greater than VGS minus VT, which we have seen in the previous slide. Okay, so this is signal current in the drain terminal. So what will be the signal current in the drain terminal, and we have the various expressions derived for the transconductance. Okay, so here ID is represented where we have the expression given, and VGS is very much is less than 2 of VGS minus VT, and I can approximate the ID to be the drain current, which is the DC current, and ID, which is your AC current. And of course I, the caps D in the suffix refers to the combination of AC current and the DC current of a drain. Okay, and similarly I can derive an expression for a transconductance. So where you could see the transconductance to be 2ID by the overdriven voltage. So total instantaneous voltage VGS and VD. Okay, so from this you can see here it has been plotted for VGS, okay, over the time, and here you can see the waveforms, that is the positive and the negative peak is determined over here, and similarly in both the cases it has been determined, and the approximations are given to be a total instantaneous voltages both for the drain drain voltage as well as the gate source voltage. Okay, so similarly I can represent in the small signal pi model also for the MOSFET. Okay, so here this is your diagram depicts the voltage gate source as well as the current flow, which is the current source, right, GMVGS. Okay, so similarly here also it is mentioned with the output resistance added at the output side. Okay, so similarly I can represent a T model. Okay, so as we have seen in the BJT, here it represents a T model. You can see the circuit has been replaced with a T type, and here this is for P type and the N type MOSFET. So these are the hybrid pi model, and this is the T model represented. Okay, thank you.